and if the fault is not detected, then it should be what? So we already know that it is not F3. And we apply T2 and we don't detect a fault, so it must be fault F1, right? Do you agree? Otherwise, it has to be F2. Do you agree? You have to think for a minute. You apply T1, and you know that it is given that there is a fault, and there's only one fault. And you apply T1, and you find that it does not detect a fault. So what would be your conclusion? The conclusion has to be that it is fault F3, because if it was F1 or F2, the fault would have resulted in detection, right? And so we know that if it is detection, then it is fault F2. And if it is not detected, that means either F1 or F2. And then you apply T2. And T2, let us assume it detects a fault, then it has to be F2. If it does not detect, it has to be F1. So basically, we can say that here, notice that if it is fault F3, you only need to apply a single vector. If it is F2 or F1, you only need to apply two vectors. Whereas in case of the preset approach, you were going to apply all three vectors. So obviously this is a more efficient approach, but here's an interesting question. Can you calculate the average number of tests needed for fault distinction? Okay, does everyone know the meaning of the word average, which in statistical terms is called expected? So what is the expected number? So sometimes it is going to take 1, sometimes it is going to take 2, right? Now assuming that each fault has equal probability of being present, now here we are getting into a use of probability theory. Actually, we are going to look at probability theory later on, but we haven't done that formally. But since you guys have taken some probability theory and statistics, so let us try it and see if you have any questions. Assuming equal probability, for each fault. And that means, since it is given that a fault is there, it could be either F1 or it could be F2 or F3. So, probability of a fault is 1/3. Okay, so your expected number, the answer that we are looking for, so the average number is equal to how many vectors it will take if it is a fault F1. If it is fault F1, we are going to take 2, right? how many vectors it will take if it is fault F2? 2. And it's just 1. And if you calculate this, it will turn out to be 1.7 vectors. Average, the expected number. So in general, if you do adaptive testing, it's going to take sort of less than 2 vectors. That's the expected value. And as opposed to a preset case, when you were applying all 3 vectors. So basic idea is that if you are prepared to use some intelligence as the process is going on, you can optimize the performance of your fault distinction problem. Now there is another approach that is used for fault distinction. Guided probe approach for fault location, which works for both hardware and software. Now, until now, we had assumed that whatever you are testing, you can access the inputs and outputs, but you cannot get in. If you can get in inside a hardware unit, then you can use some kind of guided probe, so you can trace maybe the error, and you find that here, at this point, things seem to be working okay. And later, you find that at this point, there seems to be some error. And then you will conclude that there is somewhere between here and here that something is going wrong. And in hardware, sometimes it is allowed. You have a board, and sometimes you have a probe, and you probe these chips, and you can possibly identify which particular chip it is. But in hardware, it takes a bit more work, because you actually have to open it up, you have to probe, and which is not always possible. But in software, it is actually easier, because in software, you can always go in, and you have these integrated development environments, and that basically allow you to probe inside the software. You can put breakpoints in software. You can put a breakpoint here, you can put a breakpoint here, and at this breakpoint you may find that the state of the software is good. At this point, the state of the software is bad. So you assume that there's somewhere between here and here, there's a bug. So that is the guided probe approach, which is actually a powerful technique, but we are not going to analyze that. And that is the end of our discussion on testing of combinational circuits. Incidentally, is software like a combinational circuit, or is it like a sequential circuit? Maybe we'll come back to this question later. Let us come to sequential circuits now. Now, testing a sequential circuit is a bigger challenge, because to test a sequential circuit, you need to initialize it into a known state. And then you need to apply a test sequence long enough that will going to sensitize the fault and propagate the error to the output. Now, if it is a sequential circuit, it may take a few clock cycles for you to be able to sensitize it, and it may take a few clock cycles to propagate the error to output. And if you have n flip-flops in a circuit, then with n flip-flops, you have 2 raised to n states. And so you have if you have a state diagram, you have these 2 raised to n states. And however, traveling from one state to another state is not always allowed. You can typically go from one state to some specific states. So, and of course, if you want to go from some state A to some state Z, somewhere here, then you have to go through some intermediate states, and you can get there in many different ways. And so you have numerous possible sequences. In general, testing a sequential circuit is a difficult problem. And the usual approach, it can be done. So we have seen D algorithm, and there is a version of D algorithm that you can apply to sequential circuits. The only thing is that so far we have seen D algorithm that you just start with the inputs and go towards the outputs. Now, if it is a sequential circuit, you need to somehow, at the site of the fault, get a D or D bar, and it may take a few clock cycles. And then, in order for you to be able to move the result out, it may take you a few clock cycles. And there are examples that you can find in the literature. And and sometimes I do an example, but I'm going to skip that. It is actually quite interesting how you do it, but it's challenging. So the usual approach is that common approach is to basically take what did they say? Take the path of least resistance. So transform the problem so it becomes a simpler problem, and reduce the problem to testing a combination circuit. And this is the common approach used in hardware. But let me mention here that even though we are talking about hardware, this is actually also a significant challenge in software, because the software behavior in many cases is represented in terms of a state diagram, and then there's a question of how much you should test the software. One approach is that you test it so that you can go through each state at least once. And sometimes a better measure of how much you have tested is that make sure that you have taken every single transition from each state, and that type of verification, and that will apply for both hardware testing and for software testing.